Alright, now that we know how to evaluate definite integrals, we want to look at what does the answer to a definite integral mean? Does it have a particular meaning with respect to a given situation? So we're going to begin just by looking at some situations that are somewhat familiar. And the first one is a position-velocity situation. The graph on the left is a position time graph. Over a 4-second interval, we're covering 40 meters. Now what I've done is I've taken this position function and I've created its velocity graph. Since the slope of the tangent lines on the position graph is always 10, our velocity will be 10 all the way across, constant. And we know from our study of motion that if the velocity is positive, our position is increasing, which means our particle is moving to the right. Now what is the connection between these two graphs? Specifically, the area under the velocity graph with respect to the position graph. So if I set up a definite integral to represent the net signed area on the velocity graph, definite integral from 2 to 6 of velocity, I know by the first fundamental theorem that my antiderivative of velocity is position, so I get s of 6 minus s of 2, which represents this distance here. So this distance here is equivalent to the area shown here. That's how the two graphs are connected. And we know that the meaning of our final position minus our initial position is displacement. Just to go through the calculations here and just show a few other connections. So we know that s of 6 minus s of 2 from this point of view is 40 meters. From this point of view, the area under the curve, I have a rectangle which is 4 seconds wide and 10 meters per second high. So if I multiply those to get the area of the rectangle, I can see that the seconds cancel out and I'm left with my final units in meters, 40 meters. So in general, the definite integral of velocity on an interval a to b is the displacement of the particle over that interval. Okay, now let's make the situation a little bit more complex. So I have a nonlinear graph. I have position increasing and decreasing, which means I have sections of positive and negative velocity. So what I've done with my position graph is I've constructed from it the velocity graph. So for example, the velocity is 0 at time c and d. I have a positive velocity from a to c because s is increasing, but my velocity is decreasing, so I see a decreasing velocity here. Negative velocity between c and d, negative tangent slopes, which equates to that, and so on. Now we've already established that the ending position minus the beginning position is the displacement, and that's still going to be true. If we subtract this value from this value, we're going to get displacement, and that will be represented by the net signed area here. Okay, so we have some positive areas and we have a negative area. The positive minus the negatives, that value will equate to the displacement here, as we talked about before. But what if I wanted to get the total distance traveled by the particle? So I'm just going to clear my graphs off. Because the particle is changing direction, to get distance, what I'm going to have to do is look at the distance from this point to this point, and then from this point to this point, and then from this point to this point. Make all of those sections positive in quantity, since distance is always positive, and add them up. Alright, let's just write out what this would look like symbolically. So I'm going to have to do the position at C minus the position at A, which is going to turn out to be a positive quantity. Alright? Then if I do my ending position between C and D, S of D minus S of C, the problem is this is a negative quantity because S of D is smaller than S of C. So what I'll have to do is subtract that in order to make this quantity positive. And then S of B minus S of D will be positive already, so we can just add that on. We've discussed calculating distance this way from a position graph in the past, but now how does that connect to what I see on my velocity graph? Well, this section is represented by this definite integral, this section by this definite integral, and so on. So just to bring my velocity graph back into this definite integral is represented by this area. This definite integral is represented by this positive area. And as we said, this area is the negative, and so we have an extra negative in here to counteract that. And so you could think of this section below the axis as being positive. If we flipped it up, then this whole thing would represent the absolute value of velocity. Because remember that the absolute value of the velocity graph would mean that the bottom sections are reflected above the horizontal axis, like so, and then each of these areas in red would represent a positive area. So in general, we can say, based on what we've just talked about here, that distance traveled over AB is the definite integral from A to B of the absolute value of velocity. Okay, now one final question with respect to motion. What would I get if I did the definite integral A to B of acceleration? A couple ways I could think of this. These are my individual rectangles in my Riemann sum. The height would be the units for acceleration, which are meters per second squared. Every individual width would be seconds. So since we're doing area, if we multiply these two units, length by width, our units on our final outcome should be meters per second, because the seconds will cancel out. So our unit should be velocity. Well, we know it's going to be velocity because we know that the antiderivative of acceleration is velocity. And then by the first fundamental theorem, we have the velocity at B minus the velocity at A. So what you're hopefully beginning to see is that the definite integral of a rate of change gives you the change in the antiderivative of the quantity you're integrating. Alright, let's look at one more example with respect to this. This time we have r prime of t, which is the rate, which would be an instantaneous rate, at which rate is falling in millimeters per minute. So right away, just to look at this in a variety of ways, if this is my derivative graph, my r prime graph, and this is measured in millimeters per minute, and time here is in minutes. Again, just to understand this question, let's set it up in terms of a rectangle. This would represent the net signed area under this curve. And so our units would be length times width, millimeters per minute, multiplied by minutes. Now if we didn't have a nice shape here, what we would have to do is break this down into individual rectangles and do a Riemann sum. But we'd still be doing length times width and summing them up an infinite number of times. And so the sum of our units would still be, in the end, in millimeters. Alright, so the outcome of this is going to give me a quantity in millimeters. If I apply the first fundamental theorem, the antiderivative of r prime would be r of t, as t goes from 0 to 10. So that would be r of 10 minus r of 0. And what would r represent? R would represent, since r prime represented the rate at which rain is falling, r would represent the amount of rainfall after time t. So the amount of rainfall at the starting point subtracted from the amount of rainfall up to 10 would give you the change in the amount of rainfall over the 10 hours. Or to put it more simply, the amount of rain received in the last 10 hours. So just to generalize our findings, if we do the definite integral of a derivative, what we will get is the change in the quantity of the antiderivative of f prime, which is f, over that interval. And so a definite integral is giving us the change in the antiderivative of the quantity being integrated over the time period. Now, by the way, this statement up here is sometimes also written with f of b isolated. So we could say f of b equals f of a plus the definite integral. And you might say, well, what's the use of that? F of b is our quantity at the end, if we think of f as the quantity of something, okay? F of a is the starting amount. The definite integral is the change. So if you think of the starting amount plus the change, you're going to get the final amount. And if you want to take that just one step further, f of x is equal to our starting point, f of a, plus the change from a to x of f prime, and I'm going to use t here to distinguish between t and x. So the starting point plus the change equals the value we're at. Alright, and just to summarize even one step further in terms of making this general, the antiderivative of any function is the change in that function's antiderivative. If you're integrating a rate of change, you're going to get the change in the quantity, whose antiderivative is the derivative of this. In general, the definite integral will give you the change in this function's antiderivative over the interval a to b.